Okay, let's start. Hello, everyone. Welcome to Seattle Entrepreneurship Club's weekly MIC event, and I'm your host today, GMA. Before we formally start this meetup event, let me briefly introduce the event host, Seattle Entrepreneurship Club. The Seattle Entrepreneurship Club, SEC, is a non-profit organization founded in April 2008 by a group of professionals and entrepreneurship enthusiasts in the Greater Seattle area. SEC's mission is to unite high-level entrepreneurial talents and teams from around Seattle to North America to build a platform for networking and collaboration among entrepreneurial talents and teams, entrepreneurial investors, and professionals in all fields, and to help them succeed with a variety of services. At the same time, SEC also focuses on cooperation with organizations of different industries and sectors in China and the Seattle area to promote exchange of enterprise, talents, and cultures between China and the United States. SEC has been hosting a variety of entrepreneurial-related events, including annual entrepreneurship competitions and weekly entrepreneurship meetups. At the same time, SEC has also hosting a wide range of entrepreneurship assistant programs and a national-wide event with partner organizations. We welcome you to follow SEC on WeChat and LinkedIn page to get the latest event information. And in today's event, we're very glad to invite our main speaker, Mr. James Marr, the VP of Technology from Rapid Data here today. James has more than 20 years of data analytical experience with a focus on big data technology and the modern database software research and development. Prior to joining Rapid Data, James had worked with many well-known international companies such as GM, Sun Microsystems, HP, Crayon Data B2B, and Disney R&D Center of North America. As the R&D Manager of Disney, he led his team and helped the company develop and implemented a big data analytic platform for log analytics for Google from ground up. Now, as the Vice President of Technology at Rapid Data, James is deeply involved in the research and development of the Rapid Data platform, an integrated real-time, AI-based big data insight platform designed by Rapid Data. He has created the product development roadmap and led the international R&D team in his efforts to innovate products and solutions to meet new big data challenges and the technical requirements of modern data systems in many industries. Today, James will share his technical insights on building a modern real-time distributed big data analytics platform. The agenda today, we will first invite Annie Zhu, the Director of Marketing from Rapid Data, to give us a brief introduction of Rapid Data. Then James will share his experience and insights in Rapid Data. After that, we will have a short QA session. James will answer selected questions from our audience today and our WeChat discussion groups. Please feel free to ask your question in the QA panel during our today's presentation. Okay, let me first welcome Annie to introduce Rapid Data. And James, you can share your screen now.
Yeah. Can everybody see that?
Yeah.
Yes, I can see that.
Yeah.
Okay, great.
And you can enter the full screen mode. Yes.
Right.
Thank you. Yeah. So, okay, I'm going to start. Good evening, everyone. Thank you for joining us for tonight's online meetup. My name is Annie Zhu. I am the Marketing Director for Rapid Data. First of all, I would like to give you a brief introduction to our company. So Rapids Data was founded in 2014. Our Chinese headquarters is in Beijing, and our US headquarters is in Silicon Valley. Our company specializes in the research and development of real-time big data analytics, providing innovative and advanced big data technology, products, services, and total solutions to help our clients extract valuable insights from their data to support real-time business decision-making. Currently, we have about 100 employees, and most of them are working at our global R&D centers located in America, Australia, India, and many cities in China. We have successfully completed many projects in China so far. Recently, China Mobile awarded Rapids Data the tender to upgrade the Inner Mongolia information technology infrastructure to support the rollout of 5G service. Last month, we signed a strategic cooperation agreement with the Shanghai local government and the Shanghai ST Venture Capital Group to build a big data technology demonstration site in order to develop a big data application ecosystem in the Shanghai Jiading district. We are very excited about these new projects and looking forward to another profitable year. We think two important factors contributed to the success of Rapids Data in China. One is that we have a very international team. Many R&D team members used to work for world-renowned big tech companies and research institutions, such as HP, Oracle, Tandem, Sun, IBM, and others. Some of our experts have more than 20 years experience in advanced big data technologies, such as massive parallel processing, in-memory distributed computing, modern database data warehouse development, etc. Some of our experts are US patent owners in the related fields. Our team was the first to completely implement and deploy the massive parallel processing data warehouse technology in China. We have also partnered with many prestigious Chinese universities and research institutions, such as Renmin University and the Chinese Academy of Science, to train and recruit young talents to bring fresh and innovative ideas to improve and expand our product line. Another attribute that differentiates our company in the Chinese market is that we really focus on our business model on the development of in-house proprietary products and IP. James, maybe you can turn to the next slide, please. Yeah, so our core product, the Rapids Data Platform, which is a fully parallel, distributed in-memory federated query system, was designed from the ground up. So the ability to write our own code empowers Rapids Data to continuously optimize the performance of our products without the limitation imposed by third-party developers. It enables us to provide tailored products to different clients with different big data challenges and data system requirements. Furthermore, Rapids Data is a member of the International Organization for Standardization. We drafted and submitted the SQL 9075 2018 streaming database international standard to ISO in 2017. The standard was accepted and became officially effective in 2018. And our submission of the AI in Database Artificial Intelligence International Standard is currently under review. By actively participating in the formulation of international standards, we believe that we will gain competitive advantage in the global markets. So although we have achieved many milestones in the Chinese market, we truly consider ourselves an entrepreneur in the US. Currently, we are exploring this new market and hope that we will be able to transfer our success in China to America. So at the end of this company briefing, I really would like to take the opportunity to thank Seattle Entrepreneurship Club for offering such an excellent platform for Rapids Data to share our industrial knowledge and at the same time, let us learn from peers on the subject of advanced technology development and company building strategies. Thank you.
Okay, thanks, Annie, for introducing Rapid Data. It is very impressive to know Rapid Data's data analytics platform achieved so many successes. Then next, let's welcome James Marr, the VP of Technology from Rapid Data, to share with us his technical insights on building Rapid Data's modern real-time distributed big data platform. Okay, time is yours.
Thanks. Yeah, thanks, Meiji and Annie. Okay, so today my talk is building a modern real-time distributed big data analytics platform. So again, I didn't really put a traditional, like a listing of the chapters. So really, I'm just going to talk about the tech side in building how to build a modern real-time distributed big data analytics platform. Why I chose this topic is actually, this is really a sequel to my previous session, previous webinar, which is I talked about the past, present, and future of big data and database technologies. I kind of retrospectively went through the history of what is data and the big data, right? And what is relational versus NoSQL database, and the evolution of OLTP and OLAP databases. So kind of some background are being laid out. So today I just really want to give you some flavors of the technologies, some of the insight thoughts I got being involved in developing this product. And also, I think it's very important is that, especially to, because SEC is an entrepreneurship club, right? So when you start up a company, start a product, technology is also, I mean, besides marketing, besides your client base requirements, strategies, technology, how to choose technology, right? And what are the main challenges your product is facing, and how to address, how to choose the technologies to address those issues and really build the features of your product is also a very important consideration. So that's why I chose this topic. Okay, so yeah, so just as I mentioned, there's a first session before this. If you guys are interested, you can search on YouTube. I think it's been out there. Yeah, you can search this EC Weekly Talk. It's wonderful talks. Mine is open on that. Okay, so I took slide from that talk, my previous talk, which I sort of envisioned what is the new generation of database technology, right? What is the next? It's like pretty much review the history, the current status. So what is the future? So it's hard to really look into the long future, but I think quite imminently we see what is seen, right? What is seen, not just CPU, right? GPU, and kind of new generation of hardware, FPGA, like Xilinx, those kind of vendors, and XPU. You see like Google produced hardware which can support the tensor calculation, like their AI machine learning framework TensorFlow. So they used a specialized XPU, right? Tensor, sort of supporting tensor at calculation at the hardware level. That really is a new trend we're kind of seeing. And also NVIDIA's GPU, right, which is used to be used for video, but now because of its capability of flow point calculation and high concurrency capability, so people using that for artificial AI sort of computing, right? So on top of that, we can on top of this new generation of hardware, I kind of envision that we're going to have a so-called a virtual appliance core, which can really utilize the capability of those new hardwares, and then on top of that, I'll make this brief because you guys can't view my previous webinar because I talk about that more detailed. So on top of that, we're going to see, I envision that we're going to have more capabilities especially in in-memory computing, high performance computing, distributed computing, and streaming computing, etc. All right, and today, because the technologies of database is really sophisticated. There are a lot of different aspects, right? So I have kind of to choose a slice from all those sophisticated technologies because there's no way I can talk about all of those today. So I'm going to take a really important and basic slice, which is the query, right? So and in the new generation of that big data platform, I think one of the most important is distributed computing. Why? It's because pretty much on this slide you can see, pretty much I would like to say big data. You have to use distributed computing. It's sort of a must. The reason is because so to think traditionally, right? You have big data is what? 4Vs, larger volume, larger varieties, etc., right? 4Vs, those characteristics of the big data. And how do you handle the big data, right? Not just the volume, the speed, variety, everything, right? So one thing is you upgraded your platform, which means more CPU power, more memories, right? But that is so much only so much you can do because you cannot upgrade to to like maybe 256 gig or 512 gig or a 1T memory. And there's so much you can add, right? And then it's not like the cost is not really linear because when you add more power into your platform, your hardware, whatever, the cost is really high rocketing. Okay, so I think one big innovation, which actually kind of trigger as triggering this big data revolution is the distributed computing, which Hadoop is one of the examples, right? Hadoop, what is the most important thing of Hadoop? It's HDFS, one of its foundation. It's a distributed file system. With Hadoop, you can what? With HDFS, now you can store data, right, in a distributed fashion. When more data come in, you just scale, scale horizontally versus vertically. You're setting more nodes into your cluster, storing more nodes. And those nodes can be, doesn't have to be high-end machines, just they call that a commodity, right? Commodity machines, which is really cheap, really cheap, and it could doesn't have to be very stable, because with cheap hardware it might have like problems, which is fine because the distributed computing gonna address those kind of issues. We're gonna get to that. All right, so I just want to visualize this. Oh, this is small, right? A small cluster of a few nodes. When you think of distributed computing, a cluster of nodes, but this is just the first step. I try to establish some kind of visual image in your mind, right? But what is the real world like? This is the real world. I'll just take one example from, I just Googled this from the internet, and this is a Hadoop cluster with 2,560 nodes. Okay, you can see, like, I'm not sure you guys ever visited like a data center. There's racks of say cores, right? Routers and with the UPS and temperature controlled. So here is like a, per rack you have 40 nodes, and they are all interconnected with here's a 10G fiber switch and a cable. Okay, this is real world. A lot of nodes. Okay, a lot of nodes. And you have cluster, not just one cluster. Maybe you have really sophisticated. The network infrastructure is also very sophisticated. You have tons of nodes here, a cluster, and maybe a virtual network on top of your network, and you have different node clusters. And not just, probably not just in one data center, right? You have geographically distributed data centers, sort of things. Okay, so I just mentioned, right? I want to take a slice. of this. So I want to really talk about is the query. Okay, so query, a SQL query. Okay, because we're talking about big data technologies, and we're talking about database technologies today. So the foundation, right? Every database is a query, a SQL query. So then, what is most also foundation of query? Most common operation is a join. I just want to give you some refresher. Maybe some of you audience here very familiar with database. Some may not. I mean, you probably did that before. Doing that today. So what is a join? A join, that's the most common, most basic operation of a SQL query, right? So a join combines rows from two or more tables, evaluating the join conditions, right? And if the rows met the join conditions, the rows are joined. Okay. So a little bit, this is verbal. So I want to visualize that. Give you that. Okay, so we're here with two tables: a team table, a country table, right? We want to join those two tables. Join on what? Join on, because they need to have something in common to be able to be joined. And that commonality is the country ID column, right? Both have the country ID column, so they can join. And this is a join. This is a query with a join. Right? Select start from team, join country on that country ID column. Right? So country ID 186 equal to the 186 in the country table, which is the United States. All right, they join together. And what is the result of that join? Okay, so the above is that join, and bottom is the join result. Now you have all of the columns, because you say select star, right? You select everything. So the join result is every columns, all the fields. Sometimes you see fields, sometimes you see columns. All of the fields, all of the columns from those tables with a country ID as a common column in the middle, right? So now you join together those two tables, and you get a new, sort of a new table, right? A join result is a new table. And you can see what some of those country ID are excluded, right? Let's take it back. You know, like country ID 1, Afghanistan. Country ID 47 is China. They are excluded. They're not. Those countries don't appear in the join result. Why? Because the team, right? The team members. There's no team members from those countries, right? So when they join, they're excluded. And also you can notice. Some of the country IDs are repeated because there are multiple team members from one country, from the United States. There are 4 team members from the United States, so there are 2, therefore, those 4 are the same country ID. Okay, this is really basic. Right? I just want to give you a refresh your mind. What is join? All right, so so I want to talk about technologies. I promised today I want to talk about technologies. So how do we implement, right? How do we implement this join? This is the very basic operation. So you really need to implement it in a very good way, right? Okay, so but you have to do things step by step. Right? In technology world, you cannot build, skyscraper, one day. You have to step by step, one level by one level, right? So the very first way of implementation you can think of is a loop join. What is a loop join? That's stupid, but that's the very the simplest and most straightforward way is you kind of take country ID from team table, right? And then you just compare. You take each one from team table, and then you go through the country table, compare with the column, each column ID which you take from team table, and see if that matches, right? So it's like a double loop. So you take 186 and you go through the country table, see which record, which row matching the country ID of 186. No, right? No. Oh, matching right at the end. Right? And then you take what? You take 12. Right? You take 12 and you go through again. Right? You just repeat that. You just double two loops and process all of the rows, and you complete it. That is really, the most most straightforward, but obviously wouldn't be the most efficient, the best way to do that, right? So then, how do we improve that? You think of how do we improve that? what is not really good here is because you have to go through, right, each country ID in the team table, and then go through country table and each column again, each row again. One improvement we can think of is can we get rid of one of those loops? Because we need to think things step by step. So the first improvement we want to do, we can think of is to get rid of at least one of the loop, right? So how to do that? We build a hash table, right? Okay, so we take this team table and we build a hash map. Okay, what is a hash map? Hash map is you take a value, hash it. Hash is like a kind of function, right? A function. You apply the function, the hash function, to that value, and you get another value, a hashed value. And a hash map is like okay, so we take country ID 12, and we calculate it. We calculate the hash value of 12, and then we 12 we're gonna pointing to somewhere, and there are actually two records here in this table, team table, with country ID equals 12, right? The employee name Ray and employee name Craig. So those two team members from country ID 12. Okay, so you can see here, right? You can see Ray and Craig. 12 pointing to those two records, and country ID 105 pointing to one team member, Alka, and 186, which is United States, pointing to 4 team members, right? Okay, so why we do that? Why we build a hash map? Because hash map allows you to get rid of the loop. Now, you don't have to loop through the team table again. Why? Because you can just take 12, right? And then you calculate it, the hash value, and boom, you're gonna find those two records which 12 points to. Okay, so you build that hash map data structure, and now you are able to get rid of the loop. So what we're gonna do is that we build this team hash map first, and then we still have to go through, right? We cannot get rid of all of the loop. We still have to go through the country table. But now what we can do, we can just go through loop once. We take country table and we go to country ID 1. The first row is 1. Country ID is 1. That's right, because there's no entry for 1 in this hash map, right? Then we skip that, and then we take 12. Boom, we found it, right? 12. We calculate the hash value, and Hashmap has like a find or lookup, operation, and what happens is the system gonna calculate the hash value of 12 and find those 2 entries for you. Okay, so then 12, and you go to those 2 and join with this 12 records, the record with country ID as 12, which is Australia. And you go through just once, right? 47, no. 105, yes, one record. 186, yes, right? You can find directly from the hash table 4 records, and then you join them together, right? So this is one improvement. So this is called a hash join, because you build a hash map to do this. So it's called hash join. Okay, so loop join, the most stupid way, right? And then hash join, we build a hash map to do that, right? Okay, so now okay, so this is better, right? This is better than the loop join. But then you're going to think, we still, I mean, this country table, you still have to look through it. And this country table actually might, because we are talking about a distributed computing, right? So this country table might reside on another node over the network. So in order to join, even if you build a hash map, you avoid like a double looping, right? But you still need to bring this country table over the network in order to join them together, right? This is not so good because, I mean, the country table is small, right? But this is just for example. But this could be huge. You know, country table might be huge table over the network. So, and also you can see in this country table, country ID 147 are excluded, right? They don't have to be brought over the network. They don't have to be because they won't be used. Right? So if you can kind of, if we can kind of, you know, exclude them, only transfer the necessary records which are going to be needed, going to be used by the join over the network. That will be a big improvement, right? Especially in the case of the big data environment, because as I said, you know, this country table is just a sample, but you know, in other cases, it might be a huge table, spread over different nodes. You know, think of that 2000-ish nodes Hadoop cluster, right? In that kind of case. Okay, how can we do that? Yes, a block join. What is a block join? As I just said, right? Because only those country IDs, only those country IDs existing in country table need to be country. Only the rows in country table with those country IDs need to be transferred over the network to be joined with the country team table, right? So what are those country IDs? Only 3, 12, 105, and 186, right? So we can just kind of, right, send those 3 country IDs and then select from the country table only those 3 records, right? You don't have to, right? You don't have to bring over the whole table over there. We just need those 3 columns, those 3 records. Okay, so once you bring them over, you can do what? You can do same thing, hash join, or you can still do loop join. I mean, if you don't want it, because I'll get to that. Because even if you have hash join in general, going to be better than loop join, but in some case, because you still need to build a hash map, that is a cost. So sometimes if the table is really small, you're gonna still use loop join. Okay, but this block join is another improvement to bring smaller amount of data over the network to be joined, right? Okay. Okay, hold on. So I'm gonna stop here. I mean, you know, we have loop join, we have hash join, we have block join. Look, things are much better. We can bring less data, right? We get rid of the one loop with hash table, and then we are able to bring less data over the network with block join. But as I just pointed out, you know, in the real world, there's still going to be a huge table, you know, because country table is really, this is just toy table. You know, this is just sample, but it could be a huge amount of a big table spread over a lot of nodes, right? So is there anything we can do further to improve that? You know, this is something I mentioned, right? Let's say we have orders table, a huge orders table, you know, spread over lots of nodes, right? Lots of nodes. And those order ID, not like a country IDs, small, already could be, could be long, very long, right? Tens of bytes, things like that. Okay, so we still need to, if possible, we would like to find a better way. Is there a way? Yes, there is. What is that? But before doing that, you're kind of thinking, right? It's sort of a, because the point is to bring less data over the network. So the point, the direction of your thinking should be really to the direction that, how do you sort of compress the amount of data, right? You compress it, or you try to how can we reduce the amount of the size of the data which need to be transferred over the network. Okay, so that's your thinking. Okay, I want to talk about this Bloom filter, right? That is some data structure which can support what I just said. Okay, so what is a Bloom filter? So you have a list of values. In this case, blue value, red value, green value, purple value. Okay, you have a list of values, right? And you hash each value in the list. Set corresponding bit in a bit array. Think of this, right? What does it mean? Which means sort of converting a value, right, a big value, a long value, to a node, to a bit, okay, to a bit, right? It's a compression. It's sort of compression, right, to a bit in a bit array, okay. So in this case, a hash. This is for just for diagramming. So you're hashing a red value, and you got this red bit in that bit array. Okay. In real world, actually, Bloom filter, you actually usually they not just do one hash function. They're going to bring in multiple hash functions. You apply like let's say four hash functions. You're going to apply A, B, C, D, the 4 hash functions over one single value, and you're going to get 4 different bits, and you set it into that bit array. Okay, not just one. For a lot of reasons, for even distribution and less false positive. I'm going to talk about that a bit later. Okay, but for just to make things easier, here you can just think of, okay, sort of you just hash one value, and you're gonna convert that value to 1 bit. Okay, so just think of that way. That's good enough for understanding. Okay. All right, and then that result array is called a Bloom filter. Okay, so you convert a list of values to bits in the array, right? Which is this is called a probabilistic data structure. Okay. How do you use that, right? First, you set that in that, and then then you need to just like a hash map, right? This is like a different flavor of hash map. Yeah, you can think of that way. So the next thing you want to do is you need to check the membership, right? So you have this, and how do you tell whether a value is in the list or not, right? So how do you do that? For example, you take the yellow value, you hash it, and then you check the corresponding bit, right, in the Bloom filter. Okay, you hash it, you check it. So it's here. It's 0 here. It's 0 here means what? Means the value is not in the list, because if it is, there should be 1 here, right? When you built this Bloom filter, you hash all the values, each value, and you set the corresponding bit in the bit array, right? You already did that, you already done that. Now you start checking, okay? You take a value, you hash it, and you're checking the corresponding bit in that bit array. If it's 0, then this value is not in the list, right? Understand? Okay. But if it is 1, means what? Means it may or may not in the list. Why? Because in this case, you know, the red, you hash the red value, you check in the bit array, right? It is 1, right? It is in, it is, right? So it's fine, it is. But you take this light blue value and you hash it, and you check that bit array is 1, So you think this blue light value should be in list, right? Because it is 1 in the bit array, but actually it is not. It is not. It is not in the list. Then why it is 1 there? Because this one was set by hashing another value. This is, you know, you're hashing the green value, and that green value, the hash of that green value happens to be the same bit in the bit array. All right. So it is set by another hashing of another value. So even if it's 1, actually it is not. This value is not in the list. This case is called a false positive, right? It is, you know, it looks like a positive, but it is actually false. It is not. This is so-called false positive. Okay. And that is also why this data structure is called a probabilistic. It's not a 100% accurate. This is probabilistic because when it's 1, it may or may not. The value may or may not be in the list. Okay, that's why. Then you're going to think, okay, it's not 100%, right? Is that a problem? Actually, it is not. It is fine. Okay, it is fine. Why? I'm going to show you why. Okay. All right. So now we have we just, you know, we talk about this Bloom filter. So the join, which utilizes the Bloom filter, is called Bloom join, and it's straightforward, right? You just kind of replace your block. Remember the block join? You just send over the list of country ID over the network, right? No, I mean, in the case of, you know, as I just said, in the case of which I showcase you, in the case of the orders, you know, you don't want to send you want to compress it, right? So you kind of just using this Bloom filter, okay? You convert the list of values into Bloom filter, which is way more efficient, space efficient, right? Because you convert one value becomes 1 bit, you know, just bits. So that's way less data to be sent over the network. Okay, so you send this Bloom filter to the other node, and then you just do the same thing, right? You check whether your country ID or order ID, whatever, are in this Bloom filter, right? Then hold on. Bloom filter is not 100, it's probabilistic, right? We just talk about that. Is that a problem? You check in the Bloom filter, right? I said it is not. Why it is not? Okay, so what's gonna happen? I mean, what is the false positive? If it is negative, it is for sure, right? Because if it's a 0, it's for sure. Okay, it's not probabilistic. Only when it is 1. So the result of that is you're probably gonna have a few, you know, a few more entries being selected, which actually is not in the list, but you, out of this Bloom filter, you think it is, they are. So the end result is like a, you know, you might have one or two or a few more rows being selected, okay, which is erroneously selected. You know, besides, in addition to 12, 105, 186, you might have, you know, maybe China, okay? selected into this as well, and then transfer over back to the country where the country table resides. But that is fine. Why is fine? Because I mean, you're gonna join, right? You send over, you send over a little bit more data than you needed, okay? But you still need to join with the hash map or loop join or hash join, whatever. Then the join result is gonna be fine, gonna be correct. Which you bring in a few more records back, doesn't hurt, right? Doesn't hurt. Okay, so that is why it's fine. You got it? Okay. Okay, let's see. I need to. Time is kind of running. Okay, so now I'm talking about I talked about the join, right? Join, and why I want to showcase. I want to talk about how what kind of like step by step, which we just can emphasize, is then when you, whatever product you're going to be building, right? When you think of those technologies, when you attack those technological challenges, I would suggest you kind of thinking that way as well, right? You try to resolve this with, with the basic way of, make it work, okay? Make it work first, right? And then you keep improving this, but not like just like a randomly improve it. You're gonna have to think of, what are the real challenges your product is positioned to resolve, right? Really bring in more values, because our product is a distributed in memory big data analytics platform, right? So that is why for this query, for this join operation, we keep improving that with all these loop hash block Bloom join. So this Bloom join actually is not really new. It was introduced. The Bloom filter concept itself was introduced by Bloom, Mr. Bloom, right? That's named after his name. In I think 1970s. But actually, Oracle only introduced into Oracle, I think 12C, Bloom join in 2011, 2012-ish, pretty late. And MySQL, very popular database, MySQL open source database, doesn't even support it as of yet. They still don't support it. Postgres does support, but not in the sense we do that. It only support sort of a Bloom index, okay. And even Oracle, the Bloom, I think it's also kind of coming as a Bloom index flavor. It's not really easy to use, not as straightforward. And also we do this. I'm going to talk about that later. We do this in an intelligent way. We're gonna the system gonna really measure and gauge what is the distribution status, what are the volume of the data, what are the status of the nodes, how many nodes in the cluster, and then decide which join algorithm we're going to be using, okay, the system going to be using. So in that sense, I would say our system is really superior in that sense. And this also brings another insight of this technology insight is that the technology doesn't have to be really revolutionary or like a brand new or really innovative. It doesn't have to be like Bloom join. It was out there, right? It was out there 1970s already. But why so many databases still don't support it, right? And we took it and we turned it into a real powerful algorithm, real powerful way of improving our performance and transfer size over the network or whatever. So again, back to the technology, the point of view of how to think of the technology, right? Because you have to start from your challenges, your issues, your real problems, and you kind of survey the landscape, right? Find what are all the technologies out there, and then you really think hard of those, and then you choose the right technology, which out there already, maybe already, and then you bring in that, and then you kind of polish it and make it really fit into your product, okay, your scenario, and then you're gonna really building something probably nobody else has been using this, because this really, if you do that, you really make the technology, you choose the right technology, and you really make the technology work for you, for your product. So that's very important. Okay. Okay, so the next thing I'm going to talk about, again, I want to take a slice. So we'll talk about the join. This is also a slide I took from my previous talk. Because we kind of envisioned, right, the next, the trend is, as the integration of heterogeneous data in the big data world today. This is already becoming pretty obvious, right? So you're gonna have, so many different data sources. You have different data technologies out there. You have different data formats, different providers, different processing modes, different storage locations, right? Just varieties, which is one of the characteristics of big data. Okay, so, but then so many different data sources, right? So a virtual, I raised this concept of virtual data source. You have to integrate, right, all these heterogeneous data sources. And this is a domain which I think a lot of things can be done. So what is then what are we doing as Reps Data, right? What are we doing right now? Okay, so before that, what are the traditional way you can think of, right? Is all these different data sources. So traditionally, right, people running ETL process, right? Extract data from all these different data sources and put into a data lake. That's a traditional way, right? ETL has been out there. Okay. So what is our answer? Our answer is a federated database. So what is that? Okay, so again, here is all these different databases, data sources. Postgres, Oracle, DB2, SQL Server, Hadoop. Just to name a few. Actually, there are more. Not even fit into the screen. And they may be databases, and they may be not. It could be even just a file, JSON file, or XSV file, or CSV file. JSON could be a document database, right? NoSQL database. It could be so. I mean, all different kinds of data sources. Okay. So our solution is so-called federation connectors. Okay, so we're gonna we build those connectors, which is part of our database platform, our platform. Okay, so this is our solution, right? Other product may have other ways, but this is ours. So for Oracle, we have Oracle connector. For DB2, we don't have specific, we just have a JDBC connector, which can support JDBC style of access to DB2, to SQL Server, and HDFS, et cetera, et cetera. Okay, so this is our solution. I think while we do that, I'll give you an explanation. Okay, so you can select from what? You can select from one query. You can join, right, from all these different data sources. That's the beauty of that structure. So we can start from right. You know, two tables: customer table, address table, residing in Oracle database. Okay. Joining a inventory table in DB2 and some sales data in probably you store it in Hadoop. All right, that's pretty much our federation means. Okay, right. So customer address table in Oracle, inventory in DB2, sales data in a CSV file, stored in Hadoop. So I'm gonna give you some more concrete example of the beauty of this structure. First example, okay, again, right, that query. So why we build this connector structures? Because those connectors are built specifically for different data sources. So they have intelligence built in, okay? And also like Oracle is a powerful database, right? So why don't we utilize that data source, the capability of that data source to the most? If the things that data source can do, why we do that, right? So we kind of, that's called a push down. So for this query, we want to run. We can actually, you know, push down that part, the customer and address. You know, let's say this parent query have that having that predicate of customer age between 20 and 30. Okay, we want to select that kind of customers, and that query, right? That part of the query, which you know, Oracle accommodating, you know, customer and address, because those two tables are in Oracle. And Oracle is more than capable of running that kind of query, right? So why not just let Oracle run that? Okay, so we just push that query to Oracle. The Oracle run that and return results back. And when we can, right, can just what? Join that query result with the rest of the other tables, right? Okay. So let's take a further look. Let's say we have a query with sales, you know, this time I'm going to talk about the predicate sales table. With sales table, the state equals CA California, and the salesman is John. In that case, because the sales data is a CSV file stored in Hadoop, right? Hadoop is just a distributed file system. It's not a database, right? So in that case, can we still utilize Hadoop to do something for our good? The answer is yes. How do we do that? Okay. So, oops. Move my. Okay, so in Hadoop, it's called a partitioned way of storing files. This is a high partition, which means, you know, because sales can be huge amount of sales data, right? And Hadoop actually stores that in multiple files, not just one file. Okay, and it stored that in a partitioned way, which is like that. You know, sales state equal. That's a real folder path with the equal sign in the physical file path. Okay, state equal AL, state equal CA, state equal CO, and then you can imagine, right? The AL related, you know, Alabama related sales data are going to be stored under there, and then California related data are going to be under state equal CA folder. Okay, so that's called a partitioned, a high partition. And then we can utilize that right, because the HDFS connector knows that it has intelligence, right, built in. Okay, so then if it sees sales.state equals CA, so it doesn't need to look into the other folders, right? It only need to look under this folder, state equals CA folder, retrieve the files residing under that folder only, right? And then apply the filter salesman equal John. Okay, so even in the case of HDFS, we're still able to optimize utilizing the Hive partitioning feature. Okay. So that's the beauty of this connector. It's not a blind connector. It's an intelligent connector built for each different data sources. Okay. All right. So now we have this. If you take a look at, you take a step back. If you look at the query, now you have you select something from where, right? That's the query. Now this kind of a federation is the from side, right? We address the issue of different data sources. And also we utilize the connector structure to put in intelligence for pushing down capabilities and etc. Right? So pretty good now, right? We have distributed capability. We have federated capability. Now we will get to we are able to generate a query plan, right, with these things in place. So what is a query plan? It's pretty much like a tree, and that's the beauty of SQL. Okay, it's the beauty of SQL because people talk about SQL as a fourth generation language, which is pretty much you specify what you would like to do without telling the system how to do that. You just say select what from what and where predicates, right? And then the system takes this query and find the way which fitting the system the best. Because different, one query, right? One same kind of query, if you issue to different databases, every database is going to do that differently. Okay, so but that's actually the powerfulness of SQL because of that. How to say declarative, which without telling the system how to do that, the system have space to choose the best strategy to get the result for that query. Okay, but then you're gonna have to. The load is onto the system itself, right? And how are you gonna do that? Because the user doesn't tell you. The user just tell you what he wants. So then that is called optimization, right? You parse the query, you break down and into get up to a query plan, which is like a tree, and then you need to optimize it, which means the best way to do that. Okay, so why it is hard? Because here is like this example is simple, right? But it's actually a very hard. It's an NP hard problem. Why? It is because you're gonna have to have a strategy which can address all kinds of. There's endless, right? Endless types of different joins, different queries, and you're gonna have like you can have subqueries embedded into query, sometimes embedded. And I saw like queries from some customers, pages of query, hundreds of columns. Okay, so in that case, let's think of like if you join table A, B, C, you join A, B, C, right? You join A and B first, and then with C, A, B, C, or you join B with C first, and then A, B, C, A. It's kind of a permutation. With 3, how much? Because 6, right? 6 combination. But what about 4 tables, 5 tables, 6 tables, right? So it's exponentially, increasing the number. That's why it is an NP hard problem. So it's not an easy problem, okay? And there's so many different relational algebra involved as well. Okay, so how conventional query optimizer works? So for a particular query, the system gonna list all possible query execution plans, which is huge. It's a huge space, search space, right? And then based on relational algebra, system configurations, parameters, table attributes, and statistics. Why? Because you need to estimate, you need to compare all these different, because you need to find the best way, right? You need to find the optimal way. And you need to know what is the cost of each query execution plan. And how do you estimate that? You need to know all these parameters, right? And then eventually you choose the plan with the minimum cost, CPU plus IO, etc. Right? The least cost. And I just said it's an NP hard problem. Conventionally, in order to attack this problem, there are ways of like a rule-based, heuristics-based. You give the system some rule. In this kind of situation, you're going to do that. In that kind of situation, you're going to do that. Things like that. There's some heuristics as well. And there are different ways: dynamic programming, genetic algorithm, greedy algorithm, simulated annealing algorithm, etc., etc., etc. Okay. So this is already pretty hard, and our system already pretty much implement these as well. But this is kind of a known world, right? The traditional, conventional database all have that, to some extent, some kind of flavor of optimizer. But in a distributed world, a new factor was introduced, right? You have a network, you distribute it, and that's even more complicated. So let me give you an example, right? Let's say you have this query, join the address, customer, inventory, and sales, which we kind of talked about in the federated case, federation case example. Okay, and now you, after some hard work, the system get to an execution plan like this. Okay, and we'll start to run it. But suddenly, this is a huge query. You involving Oracle database with DB2 as an example, right? Oracle with DB2 and sales on Hadoop, HDFS. Okay, so inventory in DB2, right? Yeah. Okay. Okay. So in this case, the execution plan is you're gonna join address and customer first from Oracle, and then join with the inventory table in DB2, right? And then at the end, you're gonna join with sales table, sales data from Hadoop. So what if network got a glitch, right? The DB2, like the DB2 system, or your connection to the DB2 system, you got a glitch, and you're running the query and you got a glitch. Then what happened? I mean, in the conventional way, it's static, right? It's static. It will surrender, right? It's done. It will throw an exception, say, hey, something wrong. This query just cannot be completed anymore. But in our case, this is we want to do something better, okay? Because something still can be done, right? This inventory is gone, but sales is still out there. So why don't we, we like reorganize, right? Reorganize this query execution plan. We can still join address with customer, right? And we can still join with sales, okay? Right? It's okay because you can reorganize. It's equivalent. There's different ways. Maybe the original way is better than, a better way of running this query plan. In the original case, now inventory is gone. DB2 database is not a reachable. So you have to join with sales first, right? And then probably when you've done that, because it takes some time, the DB2 is back. And then you can join with the inventory table on DB2. Okay, so this kind of a, behavior is, we call it, dynamic, right? Dynamic query optimization. It cannot be static, okay? You have to accommodate dynamically in a distributed environment. But let me give another example, which is also, our system. So this is an example of credit cards, right? Credit cards in query, like a credit card application query. So you wanna, there are two predicates in the where clause. You want to select the credit score greater than 600, right? And education level as college. Okay, so these two predicates, you don't really know which one is more selective, because usually you should apply the more selective predicate first. Why? Because if it's more selective means it will, it will exclude a lot of other records. Only very few records can meet that criteria. Okay, so that means that is the meaning of more selective. You apply the more selective criteria first to exclude all the other records, right? Then this is obviously more efficient way of running, running a query plan. So in this case, we can have two serial plans which are equivalent, but you don't know which criteria is, which predicate is more selective. Sometimes credit score greater than 600 is more selective. Sometimes education level equals college is more selective. Okay, so conventionally, they just, I don't think there's any good way to further optimize this kind of a situation. But in our case, this is another big scenario, representing a lot of cases as an example here. We actually run some kind of a, how to say, data mining or machine learning, because our platform also has, AI, AI in database, right? We have this capability. We can run those machine learning and AI models inside of the database. Okay, so we actually, the system can find, actually, there's a condition which can help you to tell which way is better. So what is age? So if it finds out, actually, if the applicant, the credit card applicant's age is greater than 25, is older than 25, then the credit score predicate can be more selective. That's I don't want to explain why, or maybe it's just it's just a imagined example. Okay, so the system finds out, in that case, if it's true, then you should apply credit score predicate first, and if it's false, you should apply education predicate first, right? So you just add that condition. You add that system, going to add that condition before before. It won't change the semantic of the result of this query, right? You know, you just adding one more condition. Judge, you know, check the one more check whether the age is greater than 25. Then, you know, older than 25, you go this direction. Less than 25, you know, younger than 25, go that direction. The end result is going to be still the same. Okay, so this is another example of we call a. I would still say to categorize this as a dynamic, because it really, you need to have the data, right? You need to learn from the data. You cannot learn from the query itself. I mean, just by looking at the query, this is static query. You wouldn't know. I mean, only out of the real data, you're gonna know, okay, if you add this age greater than 25, gonna help the performance of running this query. Okay, so this is dynamic as well. Another example of dynamic out of the data. Okay. All right. So hope I'm running out of time. Okay, that's almost the end. I want to just take a look back. So we have distributed. We're starting from the very basic thing, right? From the join, from the very stupid way of doing join and loop join. We keep improving. So then we have distributed capability, we have federated query. Now we have a what? Dynamically optimized, right? Dynamically optimized query plan. Okay, that's already a very feature-rich, very capable engine can do. So now I want to get to pretty much the last bit. Now we have okay. So you have this query plan. You're pretty good, right? You're pretty good out there. Then you're gonna run this, right? You're gonna run this. You're gonna run this query. And our engine was written in Java. Other systems may be written in different languages, you know, in C, maybe in C, C++, in Rust, whatever language, in Go, right? But you know, in our case, it's Java. So, okay, why I want to talk about that? Because in case of Java, okay, other product, other technologies have other you can think of other ways of improving that. But that's the last bit, last mile, is that, you know, the Java JVM has a very good feature, which is called the JIT compilation and optimizations. JIT is just in time, right? So the Java JVM Java you compile into, you know, bytecode, right? And the JVM is going to take in that code and do a just-in-time compilation into machine code, okay? And when it runs the machine code, it will actually monitor. It has another thread. This is all done by the JVM, okay? The JIT compiler. It's a JVM feature. I mean, you don't have to worry about that. It's going to do that. It has another thread monitoring the execution of the machine code, okay? And it will identify, you know, which piece of code is, you know, like run like repeatedly. They call this like a hotspot. And then the JVM, the JIT compiler, gonna automatically first identify that, right? And it will automatically try to optimize that piece of code, which it identifies as hot. So here is, you know, kind of a sample of those optimization the JIT compiler going to be doing. We'll inline some final method. We'll remove the redundant loads, you know, copy propagation, and eliminate some dead code. Those kind of a optimization. So we really want to utilize that, right? Because we are, you know, our engine written in Java, and we run that in JVM. And JVM has this powerful feature. I mean, why not we utilize that? Why not, right? But then how? How do we utilize that? Okay. How? Is that you need to run that as a program, right? Like a Java program. And but unfortunately, the conventional way of running, running a query plan, you cannot really take advantage of this, this Java JVM JIT feature. Why? Because you have a huge query engine, right? Then you kind of have this, this query plan, right? You, after optimization, eventually you chose this this tree as your execution plan, and then the execution engine your execution engine, your platform gonna, kind of walk through this, this tree, and I'm gonna execute it. But in order to utilize the JIT feature I just mentioned, you need to convert this to a program. So you get it? You're gonna have to convert a SQL query into a Java program. Okay, and then you need to dynamically, once it becomes a program, Java program, you need to dynamically load it into the JVM and run it. And then the JVM can optimize that, because if it's a query, you're gonna have a lot of loops, right? Loop, over some join or whatever. And then the JVM gonna kick in, optimize those hotspots. Okay, so, but the point is what? The point is you need to convert the query plan, spit out a Java program and dynamically load it and run it. Okay, so that's the last bit our system is doing. We call it we call this like a dynamic compilation and loading and something like that. So I'm not sure about the name yet. Okay, so I want to mention that actually this kind of technology, you probably heard of like LLVM, other systems doing LLVM. This is sort of like that kind of flavor, but it's a little bit different. It's a little bit different. And it's dynamic, right? It's dynamic, and the JIT gonna further optimize it during runtime. Okay, so that's pretty much. I would I hope I conveyed my ideas of so today's not just, you don't have to understand. Hopefully you can understand. Hopefully I explained clearly. I think this is kind of relevant as well, because big data technology is not like other technologies. Big data technology is, I think, is irrelevant in almost every industry, right? I mean, especially you guys as entrepreneur, I think it's very relevant in today's world. And also, I hope I have conveyed my idea of like when you build your product, really how to look at the technology side of things, how to choose the technology, and look inside and out, different aspects, the problems you're trying to address, and choose the right technologies, sharpen it step by step to really build a very powerful product to win on the market. Okay, yeah, that's pretty much my.
Well, yeah, thanks, James, for the great talk. I think the join operation is a very good example to start with, which is a fundamental operation in databases and seems very simple with a small amount of data, but get much harder to compute with a bigger data amount and become insanely complicated in distributed big data entry. And from this talk, we learned that there are many challenges for modern big data analytic engines, the data can not only be stored in a single machine, but also in a distributed environment, or even from different data providers like Oracle HDFS in James' example. And query can also be more and more complicated. As James' example, one customer even have a pages for even one query. So for the real world scenario, the data store and the query optimization become critical, which James shared a lot of insights in this talk, from data join optimization to dynamic query optimization to even JIT level machine code optimization. And I think before directly getting into the complicated and analytic platform implementation, I think James did very well in focusing on the fundamentals and high-level ideas, which is suitable for all level of audience to comprehend. And it is also very interesting and surprising to know that classic Bloom filter, a data structure proposed decades ago, is not yet supported by major database providers, and it is very impressive. Rapid Data successfully leverage Bloom filter in the engine. Yeah, so as we don't have much time, so we have a very quick QA, and we have already collected some questions from our WeChat discussion groups before this meetup. So one question is that how does your technology compare to HTAP, which is a hybrid transactional analytic processing system?
Yeah, okay. That's a good question. So HTAP is, yeah, as you just said, it's a hybrid transactional and analytical platform. This is kind of becoming, it's pretty new trend that, because traditionally, you either have a OLTP or you have an OLAP. You rarely, I think it kind of started with SAP HANA as sort of a, the first industry strength HTTP system. What it tried to do is that, out of your transactional database, it tried to be able to run complicated analytical query as well. So our system comparing with HTAP, I would say, first of all, I would point out this kind of a HTAP system is, there's some issues with HTAP because usually, as I just said, right, HTTP is, is a hybrid, is, transactional system plus analytics. But actually, in the real world, when you run analytic queries, your data is, usually is not limited to your transactional data, right? You're going to have to sort of join with a lot of different data sources. Okay, so HTAP will be lacking in this aspect, right? Because it tries to run, it tries to address this kind of issue by being able to be a hybrid system, right? Run both kind of queries in the same system. But still, it couldn't if the query need to involve data from other sources, right? That's one issue. Another issue HTTP system facing is usually analytical queries. Analytical queries like more traditionally like a data warehouse. So the data model, right? You guys heard of a fact table and the dimension table. I mean, data model is just different than the transactional database. So HTTP also cannot. I mean, you cannot. It can run both type of queries, but it cannot change the data model on the fly, right? So that is something HTTP kind of system are facing. So RapidDB is positioned to address the both of those kind of issues, right? So the first issue that we have this federation capability. We have connectors. We are able to run queries across different types of data sources in one query. And data model-wise, same thing, right? We're analytical in the first place. We're able to accommodate. We're actually, in Federal, which I didn't really talk, get into more details, is that we have a very capable, powerful, and sophisticated metadata system, which is going to be able to integrate the metadata from all different data sources.
Thanks, James. And another question is about data lake. As you mentioned in your talk, Rapid Data has the capability of utilizing data source from different database providers. And then how do you think of, how do you compare Rapid Data Engine with data lake?
Yeah, question as well. So data lake is more like which I depicted in one of my slides, right? So is a way of if you don't have federation capability, then traditionally those what people are going to be doing is they have to run for different data sources, right? Your data coming out of from different data sources, you're going to have to run ETL, sophisticated ETL processes, sophisticated ETL tools to extract, transform, and eventually dump all of your data into a data lake type of a kind of repository. That is really just a dump of all kinds of data. But at the end, you still need a powerful query engine analytic platform to run the query, right, against the data lake. That is one thing. And in our case, actually, we sort of at several different levels we can help out, and also we can even sort of get rid of the need of data lake in some cases because we have federation, and so we can kind of run query directly from all kinds of different data sources, right? Even without a data lake, because your data are in all those data sources. And you need to build a data lake because there's nowhere you can dump all your data. But with Reps data, you can pretty much run query from all these extract information and analytics, with the federated query from all these data sources, right? So to some extent, in some sense, you can really, if your systems, your data is not so huge, and you have pretty good data stored in all of those systems you already have, you can utilize Reps data to achieve that kind of goals. And even if you want to run a data lake, RepsDB can help in the sense of we can retrieve data, right, with federation from all those different data sources, and also run the transformation on the fly in the query, and help you to build the data lake in a lot of ways. Yeah. So yeah.
Okay, yeah, thanks, James, for answering all these questions. As we are already over time, so please subscribe to Rapid Data social medias or email to Annie using the email address showed on the screen for more questions, or for questions about today's talk, or even about Rapid Data's analytics engine. And thanks again, James, for the great talk, and thanks everyone for joining today's meetup. So I think we will see you in next week's in SEC's next meetup. Thank you. And
great,
bye-bye.
thanks. Yeah, thanks guys for joining, and